Okay, so in this problem, what's happening, this particle or an object is sliding down in this elevated end, from this elevated end, and then this part and this part, these two parts of the plane, they're frictionless, but the middle part, which is horizontal, that one has a frictional coefficient, a kinetic friction coefficient of coefficient of 0.2. So that's there, and the dimension is given. L is equal to 40 centimeter, and H is L over 2, so H basically is 20 centimeter, or L over 2. So we need to find that once this starts sliding down, this object starts sliding down from here, where it stops, how much far away from the left edge, that is from here, how much far away it stops, so at what point it stops. So what can happen in this particular scenario, when the object comes down, because this length is not much, we do not know yet, but once we do the problem, one possibility is that it won't stop here, it will here at the first attempt, so it will come down, go there, and it still has some velocity. As a result, it still has some kinetic energy, which will increase its potential energy, and it will go up to somewhere there, and then again it will come down, and then again it may go up here and then again come down. So after 2-3 times it may stop immediately, or maybe after 2-3 times. So how to know that? What we will do, we will just do that mathematically. First we need to find what is the velocity here when it comes down at this point, when it enters the horizontal plane. So initially its potential energy will be mgh, and when it comes down at this point, let's say this point A, maybe, I don't know, and this point may be B, or left edge, right edge, I don't know, maybe this point let's call, but L is for the length, so I will write A and B here. So when it reaches point A, what is the velocity? That will be, all its potential energy will be converted into kinetic energy, so its velocity will be given by, sorry, mv a 1 square. The reason I wrote 1 is it may come back here once it goes down that way, and after going up there it may come down. So it is the first at the first what should I say, initially its velocity is a1 here. Then even if it comes back there, then we will call its velocity a2 when it comes back from here again, if it does. So this one we will find first. So va1 square will be, m can get cancelled, and that will be 2gh. So h is L over 2, so this one can be written 2g L over 2, so that's gl. So va1 is square root of gl. I'm just writing it as L, though I know L is 40, but I will leave it as L. Now what we need to find is whether this one reaches point B or it stops somewhere before that in this point. So if we do that, it has already become a bit clumsy, so I will erase this part a little bit. Yeah, oh sorry, so that's H there. So yeah, so we need to find out whether it, oh that part is erased as well, whether it reaches B. So in order to do that, what we will have to do is find the velocity at B. If it doesn't reach velocity at point B, the velocity will be imaginary, so we won't get a real value that will show that it has stopped before. So what I will do, half m vb square, this one is again vb1, is the velocity at point B, and that will be equal to, this is the kinetic energy at that point, that will be equal to the kinetic energy at the left edge, va1 square, minus the energy loss due to friction, that is given by the frictional coefficient times mg times the distance traveled, which is L. because it has gone all the way. So let's see what we get there. Do we get a positive value of VB? Before that, before doing anything, we can just get rid of all the m's. So, and what I would like to do is also multiply both sides by 2. That way I will get VB1 square will be VA1 square minus 2 mu GL. So VA1 square is GL minus 2 mu GL is, mu is 0.2, so that's 0.4. So it's still a positive value, which is a good one, which is good. That means it reaches point B, and the kinetic and the velocity there, let's say the velocity there is GL minus 0.4 GL, so 0.6 GL. That's the velocity there. So what happens now when it reaches here, because it has a velocity in this direction, and because of the velocity it has a kinetic energy, so the object will go up here and the kinetic energy will be converted into potential energy, and it will reach at some height. After that, when its velocity is 0 and all its velocity is converted into potential energy, the object will come back this way and it will again come here. Now we can find at what height it reaches by just equating this kinetic energy to a potential energy, which will be, so basically half mvb1 square equals to mg, let's say uppercase x. That x will be the height where it reaches. We can solve it for x and we can find the height, but we don't need that information, because that information, using that information, we can again find what is the velocity here when it comes back. But the velocity will be same as it is now when it's going up, because all its potential energy will be converted into all its kinetic energy here will be converted into potential energy when it reaches at some point there. But after that, all that potential energy will again be converted into kinetic energy when it comes back at point B from here. So that the velocity will be the same, the kinetic energy will be the same. So we can just use this value, this value, when we are considering that it goes in that direction after coming back. So I will do that, and again I will see if the velocity here is a real value. So that means now I'm trying to find out whether it goes up to there all the way and then goes up again. So let's do that. Now I will see what is the at point A. So half m VA, let's say 2 now. So it's coming back from the right to the left, and that will be equal to what was the kinetic energy here, minus the energy loss due to friction, kinetic friction, that is mu mg and L, just like before. So this is now, again, let's get rid of all the m's, and I don't know, so let's multiply both sides by 2, so it's VA2 square, and that one becomes VB1 square minus 2 mu GL. VB1 square is, as it was here, 0.6 GL, so this is 0.6 GL, and this is still 0.4 GL, so it's still a real value. So 0.2 GL is the velocity now. It is slowing down, of course. Now the object is moving from the right to the left, so when it reaches point A, after that it will go this way up, reach some point, and then it will come down again. And again, like before, we don't need to find what height it reaches because we don't need that information. What we need is what is the velocity when it comes back this way, velocity at point A when it comes back this way. But that velocity, as we saw before, will be the same because all this kinetic energy is converted into potential energy when it reaches there, and then all that potential energy again converted back to the same kinetic energy when it reaches here. At this point there is no potential energy, it's all kinetic energy. So we know what is VA2. So we can write VA2, I don't know, should I write 3? Maybe that will be, yeah, because A2 is when it was going up, but I used the same before, so I will just leave VA2. That means when it's coming down, now from left to the right. So that velocity we know, which is, we know the square one. I didn't find the square root one. So 0.2 GL, square root of course will be just square root. So now we need to find whether this object reaches all the way to point B. So let's now again find what is the kinetic energy at point B. VB, now let's say 3 square. That would be half m VS2 square minus mu mgl, and we can see now is getting cancelled and getting multiplied by 2 both side, VB3 square. So this is becoming VA 2 square minus 2 mu GL. Now VA2 square is 0.2 GL, but this one is 2 times 0.2, so 0.4 GL. So this is becoming minus 0.2 GL. So of course our velocity now is becoming an imaginary value. That means, as I was saying previously, mathematically we have seen that it doesn't go anymore up to point B. It reaches somewhere in between. It stops somewhere in between. And that point we want to find now. So sorry, this here, so this is unacceptable, not acceptable, so it doesn't go all the way. So now we want to find how far does it go. So that will be equal to whatever the kinetic energy it had when it started, which is mv a2 square on the left at point A. That will be equal to, when it stops there is no more velocity, so basically that will be equal to just, so basically just this equation, but this VB is 0, so this one will be equal to this one. Basically that's when it stops, the velocity of the particle becomes 0 at any point. Let's say not B, at whatever point, let's say point uppercase X or something. I used uppercase S for height before, but I didn't do the I didn't find the value, so let's just forget. I will use X again. So that will be, let's say, mu mgx. That means we are saying that it goes up to x centimeter. Yeah, it should be meter, but yeah, since I am not using any value, I can use meter because L is in centimeters, so that should be okay. Anyway, so just like that, when it stops because of the kinetic friction, energy loss due to kinetic friction, and all its kinetic energy will be used up by the kinetic friction, and then it stops. So that should be understandable. M is getting cancelled, so X will be here VA2 square over 2 mu G. Yeah, that means VA square is 0.2 GL and 2 mu is 0.4 G, because mu is 0.2, kinetic mu K actually 0.2. I have always used just mu, maybe I should be using mu K because it's not mu S, kinetic friction coefficient. So yeah, anyway, I don't think I have written them all of them, but just yeah, so it should be mu K. Anyway, so here what's happened, G and G is getting cancelled, so this is L over 2. That means X is, which is distance from point B, that will be L over 2, which is 40 over 2, so 20 centimeter. So at 20 centimeter from the left side it stops. That's what that's what the result is.